Hey there, welcome. Have you ever just stopped and really thought about our numbers? I mean, what they actually are? Today, we're going to go on a little excursion, a trip to look at the numbers we use every single day, but in a totally new light. It's a journey into a different way of counting that might just change how you see, well, everything. So, here's our game plan. We'll kick things off with the numbers we all know and love. Then, we'll jump into a whole new way of counting. We'll figure out how to translate between these two worlds, uncover a really cool connection to computers, and then wrap it all up with why any of this actually matters.
All right, let's start on familiar ground, our everyday numbers, the base 10 system. It feels so natural, so intuitive, you'd be forgiven for thinking it's the only way to count. But, well, is it?
So let me ask you a question that sounds almost silly. What does the number 10 really mean? I know, your brain probably screams, it means 10. And you're right, but only in our system. See, those symbols, the 1 and the 0, they can mean something completely different depending on the rules you're playing by. And that's the secret we're about to unlock. It all comes down to this idea called place value. The number 529 isn't just a 5, a 2, and a 9 hanging out together. Nope. It's 5 hundreds, 2 tens, and 9 ones. Each position, each slot, has a value. And in our world, those values are all powers of 10. Now, why 10? The most popular theory is beautifully simple. We have 10 fingers. We just naturally started grouping things in tens because it's what we had on hand, literally. So what if we were, I don't know, cartoon characters with only 8 fingers? We'd probably count a little differently, right? So let's step into that world. Welcome to Base-8, also known as the octal system. The rules here are simple, but they change everything. First off, you only get 8 digits to play with, 0 through 7. That's it. The digits 8 and 9, they just don't exist here. So what happens when you count to 7? You run out of symbols. You have to regroup. You make one full group of 8 and have 0 ones left over. So the number that comes right after 7 is 10. Weird, right? So instead of our familiar groups of ones, tens, and hundreds, we're now thinking in terms of ones, eights, and then 64s, which is just 8 times 8. The idea of place value is exactly the same. It's just the size of the boxes we're packing things into that's changed from 10 to 8. Putting them side by side like this makes it super clear. Both systems are built on powers, but where our world revolves around the number 10, the octal world is all about the number 8. So the numerals might look the same sometimes, but the value they stand for is totally different. Okay, so we've got the rules of this new world down, but how do we actually move between them? How do we take an amount we understand in our system and write it down in this new language? Now, this is maybe the most important thing to wrap your head around. The actual amount of stuff, the quantity of dots here, it never changes. It's fixed. The only thing that's different is how we decide to group them and what name we give that grouping. Our system's default is groups of 10. The octal system's default is groups of 8. Let's make this real with the number 29. In our base 10 world, that's easy. 2 groups of 10 with 9 ones left over. Simple. But to write this in base 8, we ask a different question. We ask, how many full groups of 8 can we possibly make? Well, 3 eighths gets us to 24, and that leaves us with 5 little ones. So the quantity we call 29 gets written as 35 in base 8, 3 eighths and 5 ones. See? All right, let's try a bigger one, the number 125. First things first, what's the biggest power of 8 that can fit inside 125? That's going to be 64. Okay, how many 64s can we squeeze in there? Just 1. That leaves us with a remainder of 61. Now we just repeat the process. How many 8s can we fit into 61? Well, 7 eighths is 56, and that leaves us with a final remainder of 5. So you put it all together. 1 group of 64, 7 groups of 8, and 5 ones. That means 125 in our world is written as 175 in base 8. Now, I know what you might be thinking. This is a fun little brain teaser, but what's the actual point? Well, this is where base 8 gets its secret superpower, and it has everything to do with the secret language of our computers. The reason base 8 is so important is because of its incredibly clean, direct relationship with base 2, or binary. You know, binary, the language of ones and zeros, on and off, that powers pretty much everything digital. Turns out, base 8 is like the perfect translator for it. And here's why it works so beautifully. Think about it. What is 8? It's 2 times 2 times 2. It's 2 to the power of 3. Because of that one simple mathematical fact, every single digit in base 8 corresponds to a unique group of exactly 3 binary digits. It's a perfect one-to-one code.
An octal 7 is always a binary 111. An octal 2 is always a binary 010. No ambiguity.
And that is a game changer. I mean, look at this long string of binary. For a human, that's just a nightmare to read or remember. But because of that perfect 3-to-1 relationship, we can just chop it up into groups of 3. Each little group translates directly to a single octal digit, turning that absolute mess into a nice, short, clean number. It's the ultimate shorthand for binary.
So, okay, we've seen how Base-8 works and why it's so handy for computers. But let's get back to us. Why should we care? This is about so much more than just a math trick.
By stepping out of our cozy Base 10 comfort zone, we start to see the hidden structure holding it all together. It makes us ask questions about things we always took for granted. Like, why do we carry the 1 when we add numbers? It's because we've made a full group of 10. But when you see that exact same regrouping process happen with a group of 8, the underlying idea suddenly just clicks. It becomes so much clearer.
Before we finish up, here are a few quick facts to take with you. First, remember, the number 10 in octal means 8, not 10. Second, if a number ends in a 0 in Base-8, it's always divisible by, you got it, 8. And of course, its big claim to fame was its role in early computing as that perfect bridge to binary before its cousin hexadecimal got more popular.
Let's end with this thought. Our whole journey into Base-8 was never really just about learning a new number system. It's about a much bigger idea. That sometimes the absolute best way to understand something you've known your whole life is to look at it from a completely strange and unfamiliar angle. So, what other ideas in your world could become deeper if you just tried to see them in a new light?